Okay, so the first thing we're going to talk about the principle of mathematical induction. Okay, so basically what we know is we're given, let S be a subset of the natural numbers such that we have the following. So the first thing that we have is that 1 is in our set S. Okay. And then 2, for every K in the naturals, if K is in our set S, then K plus 1 is also in our set S. Okay, and then our conclusion here is that S is equivalent or equal to the set of natural numbers. Okay. So what we're saying is, hey, if we have this set or this condition holds, right, on all of these numbers, natural numbers, right, if 1 is in that set, right, so if it holds when n equals 1, or k equals 1, and then it holds, if we're assuming it's true for our kth, right, so for k and n, then it also has to hold for k plus 1. Okay. So in the sense of our homework problem that we had there, right, it said use part A and induction show that every non-empty finite set, which is a subset of R, contains its suprema. Okay? So our base case, which is the 1 is an S, right? A finite set, we can think about the set that contains one element, right? So that's where the 1 comes in. We show that that base case holds. Okay? Then after that, we have our hypothesis, right? We're going to assume that it holds for a set with n elements, right? Or k elements, as it's written here. And then we have to show that it also holds for n plus 1 elements. Okay? And the revision worksheet will walk you a little bit through that. Okay? And exactly how we write this proof up when we use a proof by induction. Okay. So let's prove that mathematical induction actually works. Okay, any questions? Silence. Okay, so we have this conclusion here that S equals the natural numbers. So what if it doesn't? So suppose, two-word contradiction. S is a subset of the naturals such that everything holds up here. Ooh. No, I want this. So both of these conditions hold. Contradiction. Okay, so both of these things hold. And S does not equal the set of natural numbers. Okay, so we stated our given, right? And that. So we want to show S does in fact equal the natural numbers. Okay, questions so far? So as S does not equal the set of natural numbers, we know that the set of the naturals take out the elements in S is what? Not empty. Okay, so now S is a subset of the naturals. So what does the well-ordering principle give us? There's a least element. So n minus S has a least element. M. Okay. What do we know about this element M? So we know for sure 1 is in our set S, right? Which means 1 is not in the set n minus S. So that means M has to be greater than 1. Okay. So let's consider m minus 1. So what do we know? M minus 1 if m is a natural number, m minus 1 is also a natural number. Okay. So m is the least element in n minus s. So what does that mean about m minus 1?
It's in S.
It's in S. Okay, so we've used our first condition. What does the second condition give us here? So condition 1, we used that one. Now let's use this condition. So we know k, or in this case, m minus 1 is in the set of natural numbers, right? And this should actually be here. Quick correction. This should be S. That actually will make a difference, so I'm going to go ahead and highlight that. Those should be S's. Okay. So what does condition 2 give us?
So if there's something in S, then that thing plus 1 is also in S. So if m minus 1 is in S, then that would imply that m is in S.
Yeah, so m minus 1 plus 1 is also in S. That is, our element m is in our set S. And this is a contradiction. So n take out S is empty. That is our set S is precisely the set of natural numbers. Okay, questions, concerns? Does that make sense? Have we seen the proof of induction before?
Wait, does that prove mathematical induction?
That proves mathematical induction.
Oh, but you can map it from this problem to any other induction problem.
Right, and the one thing I will say here, right, we started out with the assumption that it's all of the naturals, right? But we can also do this if our base case isn't starting at 1, right? You just start at whatever that point is. So if our base case instead was k equals 6, right? If it holds for everything greater than that, it's for everything. Questions, concerns? Worries? So much silence. Okay, I'll end that recording.